Hey, thanks. I'd like to thank the organizers for inviting me to this conference. So I actually had a hard time choosing an appropriate topic for this meeting because even though I do a lot of combinatorics, I don't do any computability. So I chose the next best thing, which is descriptive set theory and combinatorics. Actually, this is a topic in which, moreover, the Turing degrees are an important example, in fact, a motivating example of a combinatorial structure. Okay, so I hope that you will enjoy this talk. Yeah, before I begin, I should say that this is all joint work with Ming Zhao, who is a former postdoc of mine. He is now a postdoc with Su Gao at Nankai. Doesn't want to. Oh, no, okay, here we go. Okay, so this is a quick outline of what I'm going to be talking about. So I'll first talk just about the classical notion of ordered dimension, right? I'm not going to assume that people have seen that notion. So then I will talk a little bit about the Borel notion. Then I will present the main result that we have in our paper, and then I'll say something about the special case of locally countable orders, if I have time, depending on how much time I have. Okay, so first I'm going to just set some notation, okay? Because my notation might be slightly different from the notation that people in this room are used to. So by a quasi-order, I just mean a reflexive and transitive relation. Okay, and I reserve the term partial order for the strict version. So for me, a partial order is a irreflexive and transitive relation. A quasi-order is linear or total if any two things in the set are comparable. Okay, and a partial order is linear or total if any two distinct things are comparable. So if you give me a quasi-order, it induces an equivalence relation, which is just P and Q are equivalent if P is less equal Q and Q is less equal P. And if you start with a quasi-order, you can turn it into a partial order by just saying X is less equal Y, but Y is not less equal X. So this is a partial order. And you can also go the other way, right? So given a partial order, you can make a quasi-order by saying that X is less equal Y if either X is less than Y or X is equal to Y. This is a quasi-order, but you don't get back to where you started. So that's why I'm using this different symbol over here, which is less than with the equal sign below it. Because you see, if you start out with the quasi-order, you make it a partial order like this, and then you make it a quasi-order again like that, the equivalence relations are different because this thing, the equivalence relation is just equality, right, which I've written this way. Anyway, if you don't like the symbol, you don't have to worry about it too much because I don't think I'm actually ever going to use it in this particular talk. It's just there for completeness and confusion. So for a quasi-order, okay, if you have a quasi-order, it induces a partial order on the quotient, which I will also just denote by less than. Right? So if you take all the equivalence classes, they are ordered by less than. And if the equivalence class of X is less than the equivalence class of Y, if and only if X is less than 1. And I'm just going to denote that with the same symbol. Okay, so now that we are all in the same page with regard to notation, so here are a couple of examples. So the first is the Turing degrees. That's my first example. So you're all familiar with this. The associated equivalence relation is just a Turing equivalence. So the second example is functions from omega to omega ordered by eventual domination. So F is less equal G if G eventually dominates F. And the equivalence relation here is just E0. Right? Two things are equivalent if they are eventually equal. If they're eventually equal. Oh, okay. So both of these examples note are Borel orders. They're Borel orders. So just to be clear about what I mean by that, a quasi-order is called a Borel quasi-order if the underlying set is a Polish space, right? And the quasi-ordering is a Borel subset of P times Q. Okay? That's a Borel quasi-order. Both the Turing degrees and omega to the omega with eventual domination are Borel quasi-orders. Okay. A quasi-order is locally countable if every element has only countably many predecessors, right? So the downward cone of each element is countable. That's locally countable, and locally finite has the obvious meaning. So the downward cone of every element is finite. So the Turing degrees are locally countable, right? I mean, so given any real, there are only countably many things that are below it that are Turing reducible to it. But omega to the omega is not locally countable because, for example, just below the identity function, you have continuum many functions, which are all different. Okay. So now we come to the notion of one quasi-order extending another. So you have a set P, and suppose you have two quasi-orders on P. So we say that less equal extends less equal sub 0 if, well, okay, it's a bigger relation, right? So if x is less equal 0 y, then it is less equal y. And moreover, the equivalence, induced equivalence relations are the same. Right? The equivalence relations do not change. Now, if the extending order happens to be a linear quasi-order, we will say that less equal linearizes less equal sub 0. Okay, so this is what I just said, but it's worth pointing this out that for me extension just means that you know, it extends the corresponding partial order on the quotient. Right, the quotients are the same, right? So less equal extends less equal sub 0 if and only if the associated quotients are exactly the same, and if the class of x is less equal sub 0 the class of y, then the class of x is less than the class of y. So on the quotient, the associated partial order just gets bigger, and the quotient is the same. That's what extension means. Oh yeah, okay. It's worth noting here that you can also go the other way. So suppose I have a partial order on the quotient, which extends a given partial order on the quotient, then I can get a quasi-order which extends the corresponding quasi-order. So in other words, suppose I start with the quasi-order less equal sub 0. I take the quotient and I take a partial order on the quotient which extends the induced partial order. Then I can define a quasi-order on P by just saying x is less equal y if and only if x is less equal sub 0 y, or the class of x is less than the class of y. And this gives me a quasi-ordering on P which extends the original quasi-ordering, and it extends in this sense. In other words, the quotient is the same, and the partial ordering induced by less equal is just the original one that I started with, less than. Okay. So this is just basic definitions. Any questions? Anything not clear about any of this? All right. So then let's actually go to the notion of order dimension. So this is the classical notion as defined by Dushnik and Miller in 1941. So a partial order P, the order dimension, or simply the dimension of P. What do you do? Well, okay, you first take the quotient and you ask how many linear orders on the quotient do you need to intersect to get the induced partial ordering on the quotient. Okay, well, every partial ordering is an intersection of linear orderings, right? Because you can linearize just by the axiom of choice. Any partial order you can turn it into a linear order, right? And the dimension is the smallest number of it's the cardinality, it's the smallest cardinality of a collection of linear orders on the quotient whose intersection is the original partial order. Okay, and I'll use this notation Odin P to denote the order dimension of P. So this was proved actually by Dushnik and Miller in their original paper. So this is the characterization of the order dimension. It is the minimal kappa such that the quotient embeds into a product of kappa many linear orders. Okay, with a coordinate-wise ordering on the product. Right? So that is a partial order, and the order dimension of P is the minimal kappa such that you can embed P, well, the quotient of P into a product of kappa mini linear orders. Okay, so since I'm going to be talking about this in the Borel context, it is helpful to have an equivalent characterization which doesn't talk about the quotient, right? Because the quotient is typically not a definable object when you have a quasi-order like this. For example, the Turing degrees, or just omega to the omega, anything. So you typically don't want to refer to the quotient if you're doing things in a definable way. So here is an equivalent characterization which only talks about the underlying set. Right, so the dimension of P is, so it's the minimal kappa such that you have a sequence of quasi-orders on P which extend the original quasi-order, and they have the property that if X is not less equal Y, then one of my quasi-orders is going to put Y below X. So it is the minimal kappa such that you have a sequence of quasi-orders of length, kappa many quasi-orders, all of which extending less equal, so extending in my sense, so they all have the same quotient. And if X is not less equal Y, then for one of these things, Y is below X. Now, if you think about it, that is the same as saying that when you lift these things to the quotient, right? When you take all these less equal sub i's and you look at the partial ordering they induce on the quotients are all the same. When you look at the partial ordering, the orderings they induce on the quotient, their intersection is the original partial ordering lesson. Yes.
The quasi-orders linear orders or not?
Not, doesn't have to be. Right. So you see, in the classical case, it makes no difference because what you do is you go to the quotient. Each of these things gives you a partial ordering on the quotient. Just extend it to a linear order by the axiom of choice. And their intersection will just be the original partial order. Because I have this property that Y is below X as long as X is not less equal to 1. Any other questions? Okay, great. So if you've never seen this notion, here are some examples to jog your intuition. So the dimension of a linear order is 1. Okay, no surprise there. It's already linear. You don't have to do anything. So the dimension of an anti-chain is 2. Well, what do? You linearly order it one way, and then you turn it around. Right? You take the reverse. And when you intersect them, you get the empty set, which is what an anti-chain is. Okay, so the dimension of a tree is 2. That's essentially because you have the Lex order and the reverse of the Lex order on the tree, right? Which is basically going to intersect to only the things that are comparable. And if you have an infinite quasi-order, its dimension is at most a cardinality. That's pretty easy to see. And if P embeds into Q, then the dimension of Q is at least the dimension of Q. Okay, some more examples. So let's look at the case of locally finite orders. Okay, so suppose you have a P which is locally finite and it has size kappa. Right? Then it embeds into the finite subsets of kappa under subset, right? Just by embedding, which sends you send P to the collection of things below P. Right? That's a finite subset of P. So you identify P with kappa, right? And an element, given an element P, you map it to the collection of things below P. That's a finite subset of kappa. Right? So P is going to embed into the finite subsets of kappa under a subset. So the dimension of P is always bounded by the dimension of the finite subsets of kappa. Right? If you have a locally finite order, quasi-order of size kappa. So okay, so this thing is it gives an upper bound. So it's sort of an interesting exercise to see what is the dimension of the finite subsets of kappa for various kappa. Let's start with there is infinite kappa. Okay, let's start with omega. The finite subsets of omega that has dimension precisely out of naught. Why? Because every finite quasi-order is sitting in there, right? So it cannot be finite. On the other hand, it's a countable structure, so it's got to be at most L of 0. So it's precisely L of 0. Okay. What do you think is the dimension of the finite subsets of omega 1? Just guess. I don't have any price for the best guess, but just guess.
Omega 1.
Omega 1. Okay, that's too big. It's L of 0. What is the dimension of the finite subset of omega 2? L of 0. L of 0, yeah, very good. It is L of 0. What is the dimension of the finite subsets of omega 3? L of 3. So now we have some cardinal arithmetic. So if you have CH and 2 to the L of 1 is L of 2, then it's L of 1. Otherwise, it's still L of 0. So what's going on here then is a general result of Kirstead and Milner from 1996, where they precisely computed the order dimension of the finite subsets of kappa for any infinite kappa. So it's always log base 2 of log base 2 of kappa. What is log base 2 of kappa? It is the minimum lambda such that 2 to the lambda is bigger or equal kappa. Okay. And if you apply this to these, you get precisely those answers. So for example, omega 1, well, it's just a single log is L of naught, and the log of L of naught is L of naught because it's strongly inaccessible, right? And omega 2, well, it's L of 0, and then omega 3, well, you check that this is, it depends on your cardinal arithmetic, what the double log of L of 3 is. Okay, very good. Now let's look at the case of locally countable orders. This turns out to be more interesting. So this is a joint work I did with Higuchi, Lemp, and Stefan from 2019. So we showed that if you have a cardinal of uncountable cofinality, and P is a locally countable quasi-order of size kappa plus, then P has dimension at most kappa. Okay. Okay, I'll have more to say about this. So, I mean, in particular, this applies to the Turing degrees, right? Because the Turing degrees, they're locally countable quasi-order. So if they have size kappa plus for some kappa which is of uncountable cofinality, say for example L of 2, then the dimension is at most L of 1. Yeah, I'll have more to say about this. But anyway, so later, Ashutosh Kumar and I, he was another postdoc of mine, we proved that the Turing degrees sort of have a special place. Just like the finite subsets of kappa, they have the largest order dimension among all locally finite quasi-orders of size kappa. The Turing degrees similarly have the largest order dimension among all locally countable quasi-orders of size continuum. Okay. So this sort of plays the role of the finite subsets of kappa if you're thinking about locally countable quasi-orders of size 2 to the L of 0. Oh, yeah, okay. So the next slide basically says that if you look at the first theorem, all the cases not covered by the first theorem are independent of CFC. So what are the cases not covered by the, okay, if you're interested in, say, the Turing degrees, just the Turing degrees. What are the cases not covered by the first theorem? Let's think about it. So, okay, so you could have the continuum hypothesis, right? That's not covered by this. So then the Turing degrees would have size L of 1. That's kappa plus, but it's not kappa plus for some kappa of uncountable cofinality, right? It's kappa plus for some kappa of countable cofinality. So that's not covered. Okay, CH is not covered. Let me write some of these down. So CH is not covered. What else is not covered? Okay, the continuum could be, it could be not a successor at all, right? It could be a limit. Right? It could be a limit. So it could be L of 0, could be a limit. And then you have two possibilities. It's either regular, in which case it's weakly inaccessible, or it's singular, right? So those are two possibilities. And the third possibility is that it is a successor, but it is a successor of a singular of countable cofinality. So 2 to the L of naught is, for example, say L of omega plus 1. It's the successor of L of omega. That's not covered by that. So the next slide basically says that all of those things are consistent. So of course, CH is consistent. You don't need me to tell you that. But all of the other possibilities are consistent. So the dimension of the Turing degrees can be 2 to the Aleph 0 with Aleph 0 being with 2 to the Aleph 0 being weakly inaccessible. It can be equal to 2 to the Aleph 0, which with 2 to the Aleph 0 being a singular limit, for example, Aleph omega 1. And it's also consistent that it can be equal to the continuum, with the continuum being Aleph, say, for example, Aleph omega 1. Right, so all those things. So basically, this theorem, this first theorem, you couldn't have proved anything more in ZFC about the two integrals, essentially. Okay, so this is actually all I have to say about the classical case. Do you have any questions on this time? All right, so let's move to the Borel case. So now, if you try to define Borel order dimension in terms of Borel linearizations, you automatically run into the problem that most Borel quasi-orders do not have any Borel linearizations at all. Right? There's no way to Borel linearize most Borel quasi-orders. So this is related to a classical result of Harrington, Marker, and Shalaf. So P is said to be thin if it doesn't have any perfect set of pairwise incomparable elements. Okay, and then Harrington, Marker, Shalaf, they showed that the thin Borel quasi-orders, they all have to embed into 2 to the alpha. Embed in this sense, in the sense of having a order preserving mapping. So there is an order preserving mapping from the quasi-order into 2 to the alpha with the Lex order, right? For all thin Borel quasi-orders. In particular, note that if you have a linear Borel quasi-order, then it's thin, right? I mean, everything is comparable to everything else. So you certainly do not have a perfect set of pairwise incomparable elements. So all those things, you will have this order preserving mapping into a Borel order preserving mapping into 2 to the alpha ordered lexicographic. And moreover, it's two things are equivalent if and only if the images are the same. So in particular, if you have a Borel quasi-order and if you have a Borel total quasi-order extending it, then there has to be this Borel order preserving map from P into 2 to the alpha, which has these properties, right? So if x is below y, then fx will be less lexicographically below fy. And the equivalence relation will be preserved. This is just a consequence of the Harrington Marker Shalaf theorem, and the fact that the total quasi orders they're 10. Okay, so this means that so this implies that most Borel quasi orders cannot be linearized. For example, the Turing de Vries, there is no Borel linearization. But actually, so there is something here which is not directly relevant to what I'm talking about, but it's I think it's worth mentioning. So I'm going to mention it. So in 1998, Canove, he actually found a specific Borel quasi-order, which he called less than equal sub 0. I'm not going to define what it is because that's going to take some time and it's not directly relevant to what I have to say. But he showed that there is this one specific Borel quasi-order, which is like the canonical obstruction to linearizability. Right? So if you take any Borel quasi-order, then either it's Borel linearizable or it embeds this particular order that he found. Right? So there is this particular order that he found, for which there is a continuous one-to-one map from 2 to the omega into p for any p which is not linearizable, right? Which is order preserving, and this E0 here is just the usual E0. So A and B are E0 equivalent if they're eventually equal, and so on 2 to the omega. Okay, so this is not that important to what I have to say, but anyway, so there is this one single Borel quasi-order which is sort of responsible for non-linearizability. Okay, so we're not going to define it in terms of linearizations. So I'm going to take this as my official definition of Borel order dimension. So suppose P is a Borel quasi-order, the Borel order dimension of P, which I will denote by just Odin sub P of P. So that's the minimal kappa such that there is a sequence of kappa many Borel quasi-orders on P, extending less equal, such that for any x and y, if x is not less equal y, then y is less than x for one of the orderings in my sequence. This is the same equivalent characterization we had before, except I've just inserted the word Borel. Right, that's all. Okay, any questions on this? Okay, we will see an equivalent characterization in a minute.
Excuse me, from remote. Do you ask that the sequence is Borel also, or just that the single elements of a sequence are each Borel separately, let's say?
Thank you for the question. It's not uniform, so it's only just the individual elements of Borel.
Okay, thanks.
Yeah, just the individual elements of Borel. Okay. So I'm going to give an equivalent characterization now. This involves some, sort of abstract, Borel graph theory. Okay, so you will see the relevance of all these definitions in a minute. Okay, so let X be a set and let R be a binary relation on X, which is disjoint from the diagonal. So by that I just mean that X comma X is never in R. So it's just a binary relation. So think of it as a directed graph, which doesn't have any self loops. Okay. So an R loop is simply a finite sequence of elements where xi is related to xi plus 1, and then you can go back. So xk is related to x0. So you just have a sequence of things in x, right? Finite sequence of things in x. Xi is related to xi plus 1, and xk is related back to x0. Okay, so suppose you have one of these structures, XR. The loop-free chromatic number of x is the minimal kappa such that you can write X as a union of kappa many sets, none of which contains a loop. Right? They're all loop-free, and X is the union of X is their union, and it's the minimal such kappa. It's the minimal kappa you need to write X as a union of kappa many loop-free sets. Now, suppose you have the situation where X is a Polish space and R is a Borel binary relation on X that's disjoint from the diagonal. Then the Borel loop-free chromatic number of X, it's the minimal kappa such that you can write X as a union of kappa many Borel loop-free sets. Right? Borel sets which don't contain any. Okay. Now, what does any of this have? What does this have to do with order dimension? Let me see. Yeah. Okay. Okay. Let me just point out one thing before I get to that. So suppose you have just a undirected graph. Note that. Okay. So you can think of an undirected graph in this way as just thinking of R as being a symmetric relation, right? So the edge between A and B means that both AB and BA are in R. So loop free then means that implies edge free. Like if you're thinking of a graph as a structure of this form, then each of these things, for them to be loop free, they have to be anti-groups, right? In particular, because if you had an edge between A and B, well, you would also have a loop. AB would then be a loop because you would have the edge AB, and then you could go back to BA since it's symmetric. Okay. So this is related to the chromatic number. It's not, it's the terminology is not, it's appropriate. Okay. So how is this related to order dimension? Okay, so suppose I have a quasi-order. I let AP be P times P minus the reverse of the order. Okay, so I should maybe start writing some things or drawing some pictures. So AP, this is going to what? It's going to contain all PQ, where Q is not less equal to P. Okay, that's all this is. It's P times P minus the reverse which means that Q is not below P. Okay, why am I looking at this? Well, remember, these are the sort of problematic pairs as far as dimension is concerned, right? We have that if P is not less equal, if Q is not less equal P, then there has to be something in my one of my orders has to make P less than Q. That's the reason for looking at this. And now let's define a relation on this by saying, okay, P0, Q0 is related to P1, Q1 if and only if Q0 is less equal to Q1. Okay, that's a binary relation. And it's disjoint from the diagonal because of why? Because you cannot have PQ related to PQ, right? Because that would mean Q is less equal P. But we're only looking at those PQ for which Q is not less equal. We're only looking at those PQ for which Q is not less equal. Okay, so this is disjoint from the diagonal. Now, suppose that kappa is the order dimension of P. Okay, and let's say that I have a sequence of witnesses less equal sub lambda, which is a witness to this. So let X lambda be the set, well, less equal lambda minus the reverse of the original one. So then AP has to be the union of all those things. Why? Well, okay, consider something in AP. So if you have something in AP, it's a pair PQ, where Q is not less equal P. But this is supposed to be a witness to the dimension. So that means that for some lambda, so there exists a lambda, which is going to put P less than Q. Because this sequence of quasi-orders witnesses that the dimension is kappa. So if you give me any pair PQ like this, where Q is not less equal P, there is a lambda where P is less than Q, which means that what PQ has to be in less equal sub lambda, and it's not in that, so it's in X lambda. So these X lambdas have to cover AP just by the definition of dimension. On the other hand, if I had a loop, what would that mean? So that I would have that P0 is okay. So what does that loop actually mean? Let's see. So it means that P0 is less equal sub lambda Q0, and Q0 would be less equal P1, which would be less equal sub lambda Q1, and so on. And you would have less equal Pk, less equal sub lambda Pk. Qk. Okay, and it's supposed to be a loop, so I go back to P0. Okay, so this means that P0 and Q0 are equivalent in this order, because you have in the less equal sub lambda. But that means that P0 and Q0 are just equivalent in the original ordering, because this extends the original order. So that means that Q0 is less equal P0, which is not possible because we started with a pair in AP. Okay, so the conclusion is that the loop-free chromatic number of the structure APRP is bounded by the order dimension. Okay, let's look at the converse. Suppose that the loop-free chromatic number of the structure APRP is kappa, and then X lambda lambda less than kappa is a witness. So just add the pairs in X lambda to the original ordering less equal and take the transitive closure. Of course, this will be a quasi-order, right? This will be a quasi-order on P, and it will extend the original quasi-ordering because you just added some new pairs and you took the transitive closure. But we need to know that the equivalence relation doesn't change. The quotient is the same. The quotient is the same because each of the X lambdas is loop-free. Now, okay, in general, you prove that by induction. I just want to give you a couple of examples to convince you that this will work. So suppose, for example, that I had that P was related to Q by X lambda, and Q was related to R by X lambda, which then was related to P by X lambda. Then PQ, QR, or P would be a loop, right? So they are all in X lambda, right? Because they're all related by X lambda, and And well, I mean, P is less, Q is less equal Q and R is less equal R. So that's a loop. Okay, that was only if you use the relations in X lambda without using anything in the original relation. So suppose now you throw in some things from the original relation. So suppose you say P is less equal Q and Q is X lambda related to R, which is X lambda related to S, and that's less equal T, and that's X lambda related to T. Okay, so then you get a loop like this, right? So QR, that's an X lambda, RS, that's an X lambda, and TP, that's also an X lambda. And this is a loop because, well, R is less equal R, S is less equal T, that's what I have here. X is less equal T, and then you can go back, P is less equal Q, because that's what I have here. Right, so this is a loop. This is a loop. So being loop free means that the equivalence relation doesn't change. Oh, yeah, okay. And finally, if Q is not less equal P, then PQ is an AP, and so it has to be in one of the X lambdas, right? It has to be in one of the X lambdas, which means that P is less than lambda Q. Okay, so you have that, so you have the dimension of P, the classical dimension of P is bounded by the loop-free chromatic number of this structure. So the conclusion is that they're the same, right? So the dimension of P is the same as the loop-free chromatic number of this structure. So now, if I gave the right definition for Borel order dimension, I should get the equality even when I put the word Borel. And in fact, I do. So that's the first. That's the first result in the paper that I'm talking about. So if P is a Borel quasi-order, then the Borel order dimension of P is just the Borel loop-free chromatic number of this structure, APRP. And now, why is this useful? Well, because you can now prove a dichotomy for these things, which is similar to the G0 dichotomy. You see, the G0 dichotomy, if you know what that is, it's a dichotomy about the Borel chromatic number of undirected graphs. So here we have some kind of directed graphs, and here we're not looking at the chromatic number, but we're looking at the loop-free chromatic number. Right, so once you have a characterization like this, you are able to show some kind of dichotomy, which is similar in spirit to the G0 dichotomy. I want to, in the remaining time, try to explain what this is. So suppose you have a sequence of natural numbers, which is non-decreasing, and each of them at least 2. Right, so nk less equal nk plus 1, and they're all at least equal to 2. So just take the product. So you have a tree then. You have a tree where at level k, the branching is into nk many things. You branch into nk many successors. Right, that's I'm going to call that thing to be S. So at level k, you're branching into precisely nk many successors. And now, let's say that D is a dense subset of this, which intersects every level exactly once. So those of you who know the G0 dichotomy, this should look very, very familiar. G0 is just binary, right? It's the binary version of this. So I have now a dense set, a D, which intersects each level precisely once. Okay. And then now I define a relation. So B0 and B1 are related. So there is some D in D. So let's say that this thing is D, and this belongs to capital D. I look at each of these cones, and I have a relation if this part is exactly the same. So in other words, this branch over here is related to that branch. So that's one relation. So that's this D IX, that's this thing on the left, right? That's related to this thing, that's DI plus 1x. The red part is exactly the same. So then you go like this, go like that, and then you go back. That's the last one. So D and hence the cardinality of the minus 1x. That's related to B0x. That's the going back part. Okay, so this is a well, in this picture, this is what a loop of length 1, 2, 3, 4. This is a loop, sorry, 1, 2, 3. This is a loop of length 3. Right, so this is R, and of course R is this R is disjoint from the diagonal. But anyway, so that's the structure of R. And now, so we call this thing G0 as P. So this is a directed graph on TS on the branches through this tree, and the relation is just the one that I just described. It's R0. Okay, so the loop-free chromatic number of this is actually going to be it's going to behave similarly to the chromatic to the Borel chromatic number of G0. So we have this cardinal invariant covering of meager. You probably all know this. So M is the ideal of Borel meager sets. You can take any Polish space there. I've taken 2 to the omega, but there's nothing specific about 2 to the omega. If you put any Polish space, you get the same cardinal. So it's the minimal number of Borel meager sets you need to cover 2 to the omega. And it's equal to if you put the reals, or if you put omega to the omega, you get the same cardinal. Okay, so the first thing to note is that the Borel loop-free chromatic number of this variant of G0 is at least the covering of meager, and the proof is very easy because every Borel non-meager set must contain a loop. So if you've never thought about this, I will leave this to you as an exercise. It's a good exercise. Show that every Borel non-meager set, a subset of this tree, must contain a loop. Okay, and here is the dichotomy. Here is one of the dichotomies. Suppose you have a Polish space, and suppose you have any relation on this, Borel relation on this, which is disjoint from the diagonal. So then either it's then the Borel loop-free chromatic number is countable, or there is a continuous homomorphism from this version of G0 into XOR. Right, so there exists some sequence of natural numbers NK, non-decreasing, and some dense set such that there is a continuous homomorphism from G0 SP into XOR. So this is sort of the canonical obstruction to having countable Borel loop-free chromatic number. Okay, how is this related to order dimension? Well, we saw that order dimension is a kind of loop-free chromatic number. That's all it is. So using this, we can cook up a collection of quasi-orders, which will give you the canonical obstruction to having countable Borel order dimension. So these are quasi-orders with exactly 2 layers. So there are 2 levels. That's the TS times 2. This is the level 0, level 1. And now, okay, suppose I have B0 comma 0 here, and B1 comma 1 here. This is below this. So B00 is below B11 if and only if there is an edge between B0 and B1 in this graph. Right, so B0 might be this thing. Maybe this is B0 and maybe this is B1, and since there is an edge between them, B0 comma 0 will be less than B1 comma 1 in this ordering. This ordering just has 2 levels. There are no chains of length 3. Right? It just has 2 levels. So this is a Borel order, and yeah, okay. So if you look at the things of the form B1, B0, then this is actually a copy of G0 sitting inside APRP of this structure. Right, so, well, okay, let's just think about that. So B1, B0, that's in AP. Why? Because, well, B0 is not less equal. Oh my God, what did I, yeah, okay, so it's not less equal sub 0, B1. That's because there is no edge between B and itself. Right? There's no edge between B and itself. So this doesn't happen. So that's why these things are in AP. And okay, so they're related. So, well, okay, they're related if and only if B0 is less equal, B comma 0 is less equal B prime comma 1. Well, that happens if and only if there is an edge between B and B prime. So this is actually literally a copy of G0, G0 SD sitting inside APRP. So all of these things have large Borel dimension. All of these things have large Borel dimension. Each quasi-order of this form, its Borel dimension is at least the covering of it. And these are the only obstructions. So this is actually the main result of the paper. So suppose you have any Borel quasi-order, then you have exactly one of the following two things. Either its Borel dimension is countable, or there is a continuous map from this thing, from this two-layered thing, into P, which is order preserving, that's 2A, and 2B says that the fact that B1 and B0 are incomparable is preserved. Right. So here I said that B1 and B0 are incomparable. That's preserved. So F of B0 and F of B1 are also incomparable. So it's this 2B that makes alternatives 1 and 2 incompatible. So 2B makes the first and the second alternative mutually exclusive. Okay, so corollary of this, for any Borel quasi-order P, either its dimension is countable, or once it's uncountable, it jumps automatically to the covering of me. That's a corollary of this theorem. And okay, so I don't have okay, another 5 minutes maybe. Okay, okay. So, oh yeah, okay. So here's another theorem in the paper, which I think is interesting. It's not a corollary of this theorem, but it's it's just a separate theorem. It says that there is a interesting connection between having countable Borel dimension and being linearizable. Right? At first, you might think that there's no connection, but I mean, actually, there is a connection. It says that if you have countable Borel dimension, then you have to be Borel linearizable, which by the result of Harrington-Markov-Chalat then implies that there is an order preserving map into 2 to the alpha for some countable alpha with the lexicographic order. So those are the only things that could have countable Borel dimension, right? Things for which there is an order preserving map into 2. Okay. So yeah, so I mean, I just want to point out what all this implies for the Turing degrees. So combining this with my earlier results with Higuchi, Lemp, and Stefan, so the Borel dimension of the Turing degrees is usually strictly bigger than the classical dimension, right? So for example, if you have a cardinal of uncountable copinality, a kappa of uncountable copinality, and the continuum is kappa plus, and you have MA kappa countable. So that's just MA for coenforcing. That's just MA for coenforcing. Then the classical order dimension of the Turing degrees is at most kappa, right? That's the result with Higuchi, Lemp, and Stefan. And then this new result would say that the Borel dimension would then be the covering of Beager, which is kappa plus because you have MA kappa. So in particular, if you have PFA, this is kind of curious. So remember, PFA implies the continuum is of 2. So under PFA, the classical dimension of the Turing degrees is precisely L of 1, and the Borel dimension is precisely L of 2. Okay, just a few final things, which are also in the paper. So we also showed that if you have a locally finite Borel quasi-order, then its dimension is countable. This is easy. This is sort of like the classical, essentially like the classical case. The other thing is that our dichotomy, so it doesn't provide any natural upper bound on the Borel dimension of the Turing degrees other than the continuum, right? So you might wonder, is it always equal to the continuum? I mean, in these previous examples, it was the continuum. So here it is the continuum. Okay, here also it's the continuum. I have 2 to the alpha naught is kappa plus, and I have MA kappa countables. So you might wonder, is it always just equal to the continuum? So the answer is no. So we were able to show that there is a CCC forcing that with forces for every locally countable Borel quasi-order to have Borel dimension L of 1. So for example, you can take a ground model which satisfies 2 to the L of naught is L of 17, and then you can find a cardinal preserving forcing extension. Well, 2 to the L of naught will still be L of 17, but the Borel dimension of every locally countable Borel quasi-order will be precisely L of 1. Yeah, so each of these things, these P0, these 2 layer things, they're all locally countable. I mean, okay, how do you see that? Well, if you take one of these branches, well, there are only countably many nodes from D which will intersect it. And for each node in D which intersects it, you get at most 1 predecessor, right? So you have only countably many predecessors. So this B11, there are only countably many things here that it's below. Right? 1 for each member of D along this branch. So these are all locally countable orders. So in particular, in this model, the Borel loop-free chromatic number of all of these variants of G0 is L of 1. In particular, the usual G0 also has chromatic number L of 1 in this one. Okay. I think that's all I have to say, actually. Here are some references. Thank you.